Lesson 9.5, Part 2. Direct comparison tests. These are tests that we're going to use at the endpoints. And we've had this comparison before. Let me go ahead and give you an example. We would like to determine if this series of constants converges or not. The hardest part is, what do we compare it to? And you try to compare it to something that's simpler. Now, how do I know this is less than or equal to this? Well, that's because this creates a denominator that's greater than this, and when the denominator is greater, the fraction is smaller. What's nice about this series is that we know it's geometric and that the radius is 1/3. And so it's underneath a converging series, therefore it also converges. And this is how the direct comparison test is used. There's another comparison test called the limit comparison. And what we do is we take a look at the nth term of the two summations, and we take the limit, and if we find we have a constant, then the conclusion is they either both converge or they both diverge. So again, pick out a comparison that you know whether converges or diverges. If you get 0 and one of the summations converges and the other one converges, if the limit ends up to be infinity and one of them diverges, then the other diverges. Let's take a look at some examples on how this is done. So we're looking at a summation of constants here. And again, the hardest part is to figure out what to compare it to. And usually the highest power in the numerator and the highest power in the denominator are what's used. And that's what's happening here and here. Now, in the end, you can really compare it to 1 over n, because the 2, as n goes to infinity, is not going to have much effect. So here is the comparison of the two ratios. Using L'Hopital's rule, we end up getting 2, which tells us they're behaving in the same way. And because we know that what we're comparing to is the harmonic series, we know that the series that we're investigating must also diverge. Let's take a look at another one right over here. Again, the hardest part is to see what you compare it with, and usually an easier version of it would be nice. So we take the limit of the nth terms of each, and then we end up getting a limit. That tells us they're behaving in the same way. So what is this? Well, this is a geometric series, and its ratio is 1/2, so we know it's converging. Therefore, the one that we are investigating also converges. Here's another example. Again, take a look at this and try to simplify it as much as you can. Take a look at the highest power, and this will reduce to 3 over n squared, and we really don't have to worry about the 3 as n gets infinity, so this is what we would like to compare it to. And what do we know about that? We know that this converges. So if this limit, if we get a limit, then that means they're behaving in the same way. So we compare, and we do get a limit, which tells us they are behaving in the same way, and this happens to be a converging p-series, so we can conclude that the other is converges as well. And here's our last one. We want to determine whether this series converges or diverges. And this is a little different from what we've been doing before. Remember that the limit as n approaches a 0 of sine of theta over theta, as theta goes to 0, is equal to 1. I want to create this kind of limit right here. So in order to do it, and this is the argument 1 over n, I want to compare it with this. And when we do that, we're going to get this expression, this quotient expression. And we know this quotient expression goes to 1. That is a limit, which means that these behave in the same way. And what I'm comparing it to is a harmonic series. So since the harmonic series diverges, this series that I don't know about also diverges. Let's go to another test, and that's called alternating series test. But before we do that, let's talk about what the alternating series is. It alternates between positive and negative. So here's some examples. You can start with positive, and so on, or you could start with negative, positive. And I guess what we need to do is remember that an alternating harmonic series does converge. We had talked about that before, but let's continue. And here's the test. The test is, this is one of the easier tests to do. You just have to pass 3 requirements. Well, first you have to have an alternating series. And then you have to talk about the u sub n term, the one that's being added or subtracted in each case. And it has to be positive. And then the previous term has to be greater than the next term, or you can say the next term has to be smaller than the previous term. That requirement must be met. And the u sub n term must be going to 0. When this happens, we say that the series converges. Now, why does that work? Well, if you start at 0 and you add a term, then you'll go out here to the sum of 1, and then you'll add a negative, so that'll take you back, and then you'll add a positive and you'll go back, and then you'll add a negative and you'll go back, and you just keep going, bouncing back and forth, but you're always adding a smaller and smaller amount until you're adding such small amounts you get closer and closer to a limit. And that's why the alternating series works. Okay, let's go ahead and use it. And I can see this is an alternating series, so I'm going to use alternating series test. 1, do I know that this is positive? I have to say that. Number 2, do I know that 1 over n squared is greater than the very next term? And the answer is yes. Because this is going to create a bigger denominator, so the fraction will be smaller. And 3, if I take the limit as n approaches infinity of 1 over n squared, does that equal 0? And the answer is yes. If it passes all 3, then we say by the alternating series test, it converges. All right, let's take a look at this next one and determine whether it converges. Again, it's positive, negative, so I go through my 3 steps. 1 over root n is positive. 2 is 1 over root n greater than 1 over root n plus 1, and the answer is yes, because this denominator is larger, so it makes a fraction smaller, and the answer is yes. 3, the last requirement, is the limit as n approaches infinity of 1 over root n equal to 0, and the answer is yes. Okay, so when we pass all 3 requirements, we say by the alternating series test, it converges. All right, the alternating series estimation theorem, just like the Taylor series had a Taylor remainder theorem where we were able to look at error, we get to look at error with the alternating series as well. This is something that AP uses quite a bit, so I want to make sure you understand it. What does it say? Well, it says that wherever you stopped at the nth term, the difference between the sum of the series to n and the true series is going to be less than the very next term. So the very next term is going to be our error. It's the error committed when we stop the approximation. So how does this look? Well, let's go ahead and show that if I stop at 6, the partial sum of 6, then my error between that and the exact summation will be 1/7. So I'm going to write s minus s sub 6, the absolute value, will be less than the a sub 7th term. And that 7th term I'm just going to put up here, and it's really the absolute value. And so I can write the -1 to the n minus 7 minus 1, but really it's the absolute value. So all of this becomes +1, and this is 1/7. So I've proved that that's true by using the 7th term to determine my error. Now it says to find how far do we go so that we have an error less than 10 to the -3rd. Okay, so we know that s minus s sub n, and we want that to be less than the very next term, which is n plus 1, and we want that to be less than 1 over 1,000. Okay, so now this is the absolute value right here. And so I'm going to go over here and I'm going to write n plus 1. I don't have to put the n plus 1 in for the sign change part of the formula. I'm just going to write 1 over n plus 1 less than 1 over 1,000. I really probably didn't need the absolute value sign, so let me go back. So 1 over n plus 1 is less than 1 over 1,000. And then this is going to be 1,000 less than n plus 1. And this will be 999. So n has to be greater than 999. If I take my series out this far, then my error will be this amount.